let's learn about the exponential distribution and where it comes from. First, we'll give some definitions. The time between Poisson occurring events follow an exponential distribution. We can think of this as the waiting time or the inter-arrival time. And some classic examples are call waiting centers, or a call kind of servicing center. We've got people on the phone, maybe it's like a helpline for a company, United Airlines, right? Got to change your plane ticket. And people want to know, well, how many callers do we need? People working the phones. So if we know, for example, the average number of calls per hour, that's a rate, so calls per hour. And then we can use the kind of number of calls over a time interval as a Poisson process. Then we can use exponential distribution to look at the gap between calls. So we don't want to have calls coming in. We don't want to have people waiting too long on hold, et cetera. So what's the kind of average waiting time between calls that a call receiver might experience? So the exponential distribution then is similar to the geometric distribution. Let's talk about that. So if the geometric distribution, we'll make that capital just because, describes the number of Bernoulli trials until the first quote unquote success, or the time between successes then the exponential distribution describes the time or space intervals between occurrences of a Poisson process. So we could think of, this is like a kind of another definition of return period or recurrence interval, just with a different distribution. So they're very much analogous. The exponential distribution is related to the geometric distribution, but instead of individual trials, we're thinking about time and space, so continuous variable. So let's derive this a little bit, and we're going to derive the exponential distribution from the Poisson distribution. Le Poisson. So first we'll define our random variable. So that'll be big T. So let T equal the time between Poisson events. We note that T is a continuous random variable. And then let T1 be defined as the time until the first occurrence of events. All right. So we have time. We'll start at 0. And then we have some value t, and then this is going to be the time it takes to get to that event occurring at time t. All right, so then and if there is no occurrence, of the event between t is equal to 0 to some time t. Actually, we'll make that a big T. So between 0 and t. Then we can say t1 is greater than t. And according to the Poisson distribution, we can say that the probability that t1 is greater than t is equal to the probability that x t is equal to 0. And so remember, the Poisson distribution says x is the number of events over some time period t. So we're saying that we've got this time, it's t, no events happen. So we'll use the Poisson distribution to evaluate that. So no events over some time period t. Okay, now we can write that out as the PDF function. And so that's going to be nu t to the x over x radical times e to the negative nu t. So nu is our rate parameter, t is the time, and then x is the number of occurrences. So because it's 0, then we can plug in 0 for x. And so we get nu t to the 0 all over 0. And so this all ends up being 1 times e to the negative nu t. Okay, so this is what we're left with. So now we can write this out as the probability that our big T, the time it takes until the first event is greater than some value T, some, whatever this wants to be, is going to be equal to the e to the negative nu T. All right, so this is kind of an intermediate step here, where we haven't derived anything quite yet. But we might be interested in what's the probability that our time period or time interval t1 is less than or equal to some time t. Now this is starting to look like a CDF, right? So that is equal to simply the complement of this, right? That's going to be 1 minus the probability that t is greater than t, our time gap or time until the first event is greater than t. And so that is then just equal to 1 minus e to the negative nu t. So now, my friends, we have CDF. Because it's this inequality, we're interested in the distribution of time gaps. And so this is the time it takes until the first event occurs. That's big T, time until first event. So it's this complement of what we did above, and now we get a exponential CDF. So that's our exponential CDF function. And if you were to evaluate this for t is from 0 to infinity, then that distribution it's going to look something like this. So we've got big F of t, we have t over here, and it's basically going to be like this. And it's going to obviously asymptote at 1. So now we'll write that out as big F of t is equal to 1 minus e to the negative nu t. So that's our CDF. Now, how do we get a PDF? Well, take the derivative of the CDF. So our PDF function is equal to the derivative of the CDF with respect to time. So d over dt, 1 minus e to the negative nu t. And that gives us, this nu comes out and it's negative, so we get rid of that. The derivative of 1 is 0. So we end up with nu e to the negative nu t. So this is our PDF function right here. And what that looks like, and you can plot this on your own as well, but it looks something like this, an exponential decay kind of function. And if you take the integral of this from 0 to infinity, then we end up with 1. It's the way this is defined. Great, so let's look at some of the moments of this. The expected value of our time interval, our gap, is equal to 1 over nu, and the variance of our interarrival time, big T, is equal to 1 over nu squared, which if we want the standard deviation, then we just get 1 over nu as well. So the standard deviation and the mean values are they going to be the same? So now we have a new definition of an interarrival time, T. We can also think of this as a return period. As long as we set the problem up correctly, it'll be distinguished from a geometric distribution. And again, T, if we think about the mean value of T, so if our, say our rate is, we'll say 10 per 60 seconds, which we'll use as an example soon, then this is equal to 1 over 6. Then the expected value, so this is the rate, so 1 over 6 something events per 60 seconds per minute. Then the expected value of the interarrival time is just 1 over 6, which is equal to 6. So we expect to wait, in this case, 6 seconds between things happening on average.